Alright, we're going to cover a few more things about lines before we move on to surfaces. Now we're going to take a look at closed loops. So we've kind of looked at line integrals in scalar and vector fields that start at some point A and end at some point B. But now we're going to go ahead and take a look at what if the loop is entirely enclosed. So in other words, you start and then you end where you started at. Um, there's a few ideas, and the first one I'd like to take a look at is something called circulation. So, circulation is very similar to a line integral. As a matter of fact, it is a line integral, just like you would have a line integral in a vector field, except in this case, the surface or the curve is enclosed. And so what we're looking for is as we go around this curve, how much of the vector field is helping us versus how much is hindering us. That's going to create some rotation. And we call that rotation circulation because you've got some sort of circulation going on here. Now you'll notice that my vector field that I've drawn here is in the direction of the motion of travel of my parameterized curve C, which is also r of t. And so when the vector field is helping you, that's going to be positive circulation. Now, if you could imagine these arrows all being flipped to oppose the direction, that would be a negative circulation. And most curves are going to have some of both. For example, if you could imagine if my vector field all pointed from left to right with no angles to it, you would see that the circulation would be zero because if all the vector are pointing to the right, then you'll notice that as this curve goes this way, it's fighting it. As this curve goes this way, it's getting help from the vector field, and at the perpendicular, nothing as far as circulation is occurring with the vector field. So that if, like for example, if you start somewhere and go back to that spot, and the sum of all of the circulation about this is zero, what you have is a conservative field. For example, gravity is a conservative field. If I work my way up, I will lose some energy to the field, and when I work my way down, I'll gain that same energy back. And so for an example of a conservative field, maybe like gravity, where all of the forces near the surface of the Earth are equal. Well, not the forces, but the acceleration. And as you work your curve, like let's say that you move up and then you turn around and go back down to where you started. So this would be a closed curve. And you'll notice that all of the work you fought, so all of the work you fought with to get up here, you gained back that work as you go back down to where you started. So, in other words, if the circulation of a field is zero, it is a conservative field. Now let's take a look at what this looks like. So you'll remember that when we were dealing with a line integral in a vector field, we picked an arbitrary point and we zoomed in on it, and we would look at it and say, okay, we've got our dr, and then we also have, in this case, the force is almost pointing in the same direction. Then we have our vector at that point. And what we're doing is we're going to sum every single one of these for every point around the curve. And so to do that, we take the dot product of f dot dr, and we're going to sum everything in the loop. Now here's a difference in notation. When it's an enclosed loop, we're going to notate that by putting a little circle around our integral sign. And so just like with the line integrals in a vector field, we can indeed rewrite this as f dot v integrated across dt. And now what you need to do is find the points in time A and B where you start and end at the same spot. So maybe this curve starts here at time equals 0, and maybe by the time it gets back around, it's at time equals 2 pi. And so this would be our A, our starting point. That would be our B, our finishing point. And so this is circulation of this field along this curve. And so that is circulation. It's basically the same thing as a line integral in a vector field. And next we'll be covering flux. And I'll see you for that.